So let's continue on this slide. So basically, what we're going to focus on nanocomposites in which we have low concentration of, let's say, a nanomaterial such as carbon nanotube. And we're going to talk about, the first thing we're going to start discussing is how conductivity, electrical conductivity, changes with the volume fraction of the nanomaterial. And the curve you would see is kind of a very strange curve. The first time you look at it, it may sound very strange. Initially, at very low volume percentages, conductivity is very low. And it's in a polymer that is inherently non-conductive. But then at certain volume fractions, the conductivity jumps very high. And notice that this axis here is all logarithmic. So going from, let's say, 0.2% to about 1%, a little bit increasing carbon nanotube content will increase the conductivity by about 8 to 10 orders of magnitude. Obviously, the amount that it increases depends on a lot of factors, but it's typically always this high, many orders of magnitude. Now, in order to understand what is happening here, I need to open for you another document, a whiteboard. So imagine this is our composite material, and our goal is to measure conductivity between two ends. So basically, we're interested in measuring conductivity between this end of the composite and this end of the composite. So if I want to draw, so basically imagine this is part of a circuit, and the question is, what is the resistance between these two ends? So imagine at the very beginning, all of this is, and I can show it with a slightly different color, is basically a polymer. There's nothing else in it. It's just a polymer. And initially, I start to add a few carbon nanotubes here and there. So for instance, I add, and I disperse them. There's one carbon nanotube here, there's one carbon nanotube here, there's one carbon nanotube here. At the very beginning, you see that the distance between two carbon nanotubes is very large for any electron to go from one to the other. And also this distance is very large for any electron to go from this to the electrode. But now, imagine I keep adding carbon nanotubes. Still, the distance between them is very high. And then imagine I keep adding until I get to a scenario like this. Okay, and this could be many other carbon nanotubes, and now, so what you can see is that now there is a path from one electrode. There's a path from one electrode to the next. That brings me from one to the other. So electrons can go from one end to the other. So this is what we call a percolated network. And obviously you need, now this is a percolated network, whereas electrons, if they end up here, it's kind of a dead end, okay? From electrons that come from here, for instance, can go from here, can go this way, but they're not going to reach the other electrode. But there's at least one percolated network, one network that can go from one end to the other. This is a percolated network, and the volume fraction that corresponds to that is the percolation threshold or percolation threshold volume fraction, or simply percolation threshold. Okay, these are the same things. Now, the other thing that is very important to consider is that imagine I zoom in here. I zoom in this region. And so when I zoom in that region, I see, first of all, I see my matrix, and I also see my carbon nanotubes. I see one of them going this way, and I see the other one going that way. I have zoomed in, that's why the spacing looks a little bit wider. But if this is spacing from here to here, I show it with S. From quantum mechanics considerations that we are not, and I'm not an expert in that, I can show that the resistivity between these 2 points scales exponentially with S over SC. SC is a material property that we're not going to get into. It's a property of the polymer, how non-conductive the polymer is. And this, we call it the tunneling resistance, or electron. By the way, those of you who might be familiar with electron tunneling in microscopy, it's using the same principle. Basically, resistivity scales exponentially with the distance between these two. And this kind of explains the trends that we saw earlier in the experiments, that if this was the resistivity and this was the volume fraction, and the y-axis is in a log scale, initially we see conductivity is very low. It's the same as the conductivity of the matrix. But when carbon nanotubes are added, conductivity shoots up because this guy scales, because this resistance scales exponentially with distance, or drops exponentially with distance. And in a log scale, at some point you get something like this. It's not changing that much, because when the spacing between them becomes so small that they're touching each other, at some point they're touching each other, that contact resistance doesn't change much. And so after that, the change in conductivity, still conductivity goes up as you increase volume fraction. So this is volume fraction, and this is conductivity, which is 1 over resistivity. Still, even in this region, when this goes up, resistivity goes up, but the rate of growth decreases substantially because this effect has saturated. So basically now, oops, sorry. If I go back to my slides, so basically I can replace I can replace the network of carbon nanotubes that are transferring electrons from one end to the other with a network of conductive carbon nanotubes, which are just like resistors, which are connected to each other with this tunneling resistance. And that would be the conductive path through the carbon nanotube, through the carbon nanotube network, which explains this curve. So here, our tunneling is proportional to the distance. This is resistance, right? Not resistivity. Resistivity is just this part of it. Resistance is when we add the area of the contact and the distance between carbon nanotubes. The point is that the fact that we get this guy here. That's the most critical concept of this slide. So, and so basically you get a behavior that is initially here is at very low volume fractions. It's mostly conduction through the matrix, electron hopping around that is electron tunneling or electron hopping around the volume percolation threshold starts, and then it never reaches a plateau, but the change drops down after some point. So typically this is explained by an equation like this. K is a constant, this is conductivity, and volume fraction minus the percolation threshold. So percolation threshold is basically this volume fraction. This is typically a very narrow band. So like for instance, from here to here could be about 0.2%. And this could happen at around 1% or 2%. Now, what it depends on will be something that we will investigate in a minute.